Hey everyone, so about a week ago, I asked my friend to record a workshop that I was teaching for the Data Science Club. I had a workshop on deep learning, and now I'm posting it here for all of you guys to enjoy.
All right, let's get started. So, to start us off, since we're talking about deep learning, I want to ask you, before we even start off, I just want to give you a quick overview of the table of contents, what we're going to go through. It's going to be pretty in-depth, and I'm going to focus mainly on theory, because a lot of the actual programming that you'll do with libraries like PyTorch are going to be pretty abstracted away from you. You'll just type in a few lines of code, and it will just implement a model for you. So right now, I want to take the time to focus on the theory behind it. That way, when you're actually programming it, you have an idea of what is going on underneath the hood. And if any of this looks familiar to you, good. If not, we're going to learn it. OK, first, I want to ask you guys, if you've heard of deep learning before, what do you associate it with? Like any words or things or ideas that come to mind when you think of deep learning? Yes? Backpropagation, OK. You've heard of that. What about anybody else? Yes, Lance? Neural networks, that's good. That's good. Yes? Ooh, I like that one. I'm a big fan. So for me, Casey, last one. Efficiency. So when I think of deep learning, I think of this image that was generated. I just put it up on Dolly, and I generated it in a second. So when you have diffusion models, guess what? It uses deep learning. Or I thought of this wonderful tool I used to complete my homework last night. Just kidding. Which also uses deep learning. Or I think of this little video that I would love to show you guys of a little robot running around, being pushed over, and then being able to stand back up again. And then eventually, if it's able to, scoring a goal. And it learned to do this all on its own, also with deep learning. So essentially, the point here being deep learning has, Deep learning has essentially revolutionized the field of machine learning. It is used in a broad spectrum of technologies. Anything interesting that you see, or that's pretty strong, but a lot of interesting technologies that you see use deep learning. It's very widespread. So let's go into deep learning. And I want to start from a very abstract view and then get further down by the time we get into it. So we're going to treat it first as just some mathematical function. It takes in some inputs, like we see on the left side, and it outputs some other numbers as an output. We can have multiple inputs. We can have multiple outputs. The question becomes, when we treat it like a mathematical output, is how do we translate the real world into numbers that we use as a function, and then how do we translate that back out into interesting things? So one example in, for example, image classification, we take an image and we take pixel values, and we translate that as numbers. We say, OK, let's represent 0 as completely black, 255 as completely white, and here we have some notion of representing an image purely with numbers. And then the output could be what we'll call integer hot encoding, or one hot encoding. This is essentially saying, OK, it's a 1 if we predict that image is a human, if it's 0 if we don't predict it. So here it's like, OK, we predict it was a human. We didn't predict it was a dog. We didn't predict it was a cat. That's just one example. But there's broad examples across different places. You can be predicting stock prices, in which case your input would be stock prices over the last 10 years in this case, and you're trying to predict a continuous value, the actual price of the stock. Or if you're creating a chess player, maybe your input is an array which represents the current board state, and you want to output an array that says, hey, move the piece from 1, 3 to 6, 4. So that's another example. And in terms of natural language processing, we usually want to take words or subwords and translate them into numbers. And we'll have a dictionary of numbers. So now that we saw what a neural network can look like abstractly in terms of the inputs and the outputs, let's get more in detail in terms of what it actually means. And sorry, I got a little bit ahead of myself because I asked you guys what you thought deep learning was, and you gave me different amazing words. And one of them that Lance pointed out was neural networks. And essentially, when we're talking about deep learning here, we are going to be talking entirely about the model architecture known as neural networks, okay? And we'll explain what that means. But when you see deep learning, it essentially refers to some form of model which has neural networks as a main component. Okay, now we're going to start talking about what actually a neural network looks like. And to do that, we're going to start with the most essential component, and that is a neuron. And I've drawn it here as a little blue circle, and I've labeled it N1. And there are going to be some inputs, some numbers, as we said, to this neuron, and I've labeled them x1 through xn. And there are going to be some weights and a bias, which are internal to the neuron. So we have the inputs, which are external, and we have the weights and the bias, which are internal. And the output of the neuron is simply going to be multiplying each weight by each input and adding a bias at the end. So here we see W1 was multiplied by X1, W2 by X2, et cetera, for all your inputs. And at the end, there's a final bias. This might look pretty familiar for you guys because it's the same mathematical structure as linear regression. And we can see here that this is, a linear function. What do I mean by linear? Just a quick review here in Desmos. It's a straight line. We have some slope. We have some bias or y-intercept. This is an example with just 2 dimensions where you have only one input, but it could also be multiple dimensional, as we said before. So we had x1, x2, xn, and here's a visual component as well. It's still linear. It doesn't change anything at all. So that is what a neuron is. That is kind of our central workhorse, shall we say, of neural networks. And it's going to take numbers which are continuous. X1 can be anything, technically. Usually it's not like any crazy number, hopefully, but it can be anything. And then y is also a continuous real number. Okay, I mentioned linear regression, and I want to talk about it a little bit just because it's helpful to frame our thinking when we go into actual neural networks. And basically what I just want to say is usually we have some data points here, which I've just created, some mock data points. And we want to create a line of best fit. And we start off with some naive guess. And here I literally just have the line y equals x. And if we thought about our example y equals w times x, this would be referring to w equals 1. And we have a bias of 0. And here this does not do a very good job of fitting our data, quote unquote. But if we have a better example, which I've drawn here as the green line, and this is just using Desmos, it's chosen an m, which is the same thing as our weight of 1.89, and a bias of negative 1.29. And the idea here being, if a new data point shows up, it will probably show up somewhere along that line. And so as input for one of the x's, if, say, our x was 2.5, the green line would predict that the output would probably be somewhere around 3.5. And that would probably be a pretty good guess. Okay, and the idea I want you guys to get from this is that we have some inputs, and we are trying to update the weights, W1 and B, as we saw here. Up at the top, that's what we can change, and we want to make our output, Y1, be able to predict something that we care about. Okay, now that we've gone that far, I want to talk about why what we have so far is not enough. So usually what we want to do is we want to chain neurons. What do I mean by that? I mean we want the output of one neuron, here I have N1, to become the input of the second neuron. Here I have N2. So the data is going to flow across neurons. And in this case, since I just have one neuron, I have one input to the next node, which is Y1. So it'll have one weight, but it'll still have a bias. And the mathematical structure will still be the same. It'll multiply y1 by a new weight, and it will add a bias. Okay, that's all very cool, but what does that mean? Well, let's think about this. This is what we have. y2 equals w1 prime times y1 plus b prime. This is our second node. But the thing is, we already know what our y1 is, right? That is the output of the first node. Okay, let's substitute that. In parentheses, we have that y1. It was w1 times x1, w2 times x2, etc., till wn xn plus b. And we can distribute our w1 prime all the way at the left. And here we have something that looks kind of familiar. And here I've written in red that I want to take w1 prime and w1 and label it w1 double prime, which, messy notation. But the point I want to get at here is we can rename this to be its own neuron, essentially. Here we have what looks like one neuron. We have y2 equals w1 double prime x1 plus w2 double prime x2, and so on and so forth, with now a bias at the end, which is the addition of other two biases. So we thought we had two neurons, but what do we have here? We literally only have one neuron, which is neuron 2, right? It just means that the weights that represent it are something different. This is what we call a collapsing neuron. We could have hundreds in a row. It wouldn't matter. It would only ever really be able to do what linear regression is able to accomplish. So we need something else. And for that, we have nonlinear activation functions. And I've put in two up on the screen. And the idea here being, in order to stop it from just collapsing, we want to have some nonlinear structure in between each neuron. So on the left side, we have the rectified linear unit, meaning we just have y equals x, and then as a piecewise function, y equals x for all positive x, and y equals 0 for all negative x. And here at this point, so that's one. And then we have hyperbolic tangent, and that will essentially squish your inputs and outputs. So very large x will asymptotically approach, on the graph it says 2.5, I'm not sure if that's right, with super high x and asymptotically approach some negative number for super large negative values. So these are two nonlinear activation functions. And you don't have to memorize any equations, but it's just important to know that they exist and that they're important because we need nonlinearity if we want to be able to accomplish meaningful things. In other words, if all we have is a collapsed linear model, there will probably be patterns in our world which we are not able to predict. And that, at the end of the day, is what we're trying to do with neural networks. We're trying to predict values. And it might be the case that without nonlinearity, we just won't be able to see the pattern. It will be too complex. We won't be able to fit it with something linear. Okay, so now I'm going to redefine the definition of one node or neuron as I represented it earlier. And instead of just doing the linear regression at structure, which is just linear weight 1 times x1 plus weight 2 times x2 plus a bias, we're going to add this nonlinear activation function like ReLU, and then the output of that will be the actual output of our neuron. So this is essentially one node. Any questions here? I'm just going to take a brief pause before we go any further, or does that kind of make sense to everybody? I'm getting some nods. Okay, nice. Okay, now we're going to start talking about the actual topic of the day, feed-forward neural networks. And I'm going to get into what exactly I mean by feed-forward in a second. But here I just want to define some terminology. I'm going to call this a layer. And a layer is essentially a stack of neurons. Visually, we can see them as in a line, which helps us understand things. But essentially, I can have an arbitrary amount of neurons in one layer. I've labeled them 1, 2, all the way to h. And we're going to see why I put in quotation marks x1 and x2 in a second. But this is one layer. What I'm going to do is I'm going to chain multiple layers. Okay, so here I have my one layer to the left, And I have a second layer. This one has 2 neurons to the right. And I've drawn lines. I've drawn a line from N1 to N1 prime, and from N1 to N2 prime. In other words, N1 connects to every single node in the next layer. That's very important. Okay? So does N2. N2 connects to every neuron in the next layer. And so does each neuron in that layer. That's when you'll often hear fully connected. You hear like PyTorch, the way you implement it in code, it'll say a fully connected layer. That essentially means each neuron in the current layer connects to every neuron in the next layer. The important thing here, though, is that is all it connects to, which is also why we'll call it feed forward. The neurons feed forward to the next layer, but they don't connect to anything else. If there was a layer before it, we're not going to connect to any previous layers. It only feeds forward. And here, I've drawn x1, x2, xh, the point being the output of those neurons gets sent to the next neuron. So N1 prime, it takes x1 as input. It also takes xh as input. So each node at the previous layer gets multiplied by a different weight and a different bias to create the output of one of the nodes in the next layer. So there's a lot of computations happening here. You can imagine if you have layers with hundreds of neurons, every single neuron is going to be a multiplication between a weight and a separate output of a previous neuron, and that's going to happen for every single neuron in that layer. So we're having essentially lots of computations happening. Okay, that's 2 layers. Now I want to talk about neural networks in general, and you'll often hear this terminology: input layer, hidden layer, output layer. Essentially, all that really is saying is that input layer is going to be like how you represent your data, your input data, quote unquote. So for example, if I have images, I might just like to say abstractly, okay, even though it's not part of the neural network, I'm still going to call it an input layer, which is my original values, my original pixel values before they've been edited. That's going to be my input layer. And then once it starts flowing through the neural network, that's when values will actually start to get updated. They'll be multiplied by weights. They'll connect through. And at the end, we have an output layer. And the output layer is essentially the output of our model. We want it to output some value that is useful to us to predict something. And you can have an arbitrary amount of nodes which do that. Or you can choose depending on what you want to do for your task. So for this output layer, I have 3 nodes, and initially there's not really any restriction on what those values are, right? We said this is just a linear function. It could be any real number. So it could be negative, it could be positive, it could be large, it could be small. We're usually going to have some sort of activation function at the end to, or maybe not, but we will sometimes, to compress it to something valuable, but it could be any number, really. So this is feed-forward neural networks. This is essentially, when you hear deep learning, this is usually what you're going to see. Yes?
I didn't think about the question very much, so it might be really stupid, but earlier you said when you have 2 nodes that connect, they can be compressed to 1.
Right.
Why does that not apply here? Is it because they're connected between each other?
Right, so great question. This is where I kind of changed my terminology a little bit. I said that I was going to start referring to one node as a node plus a nonlinear activation function.
So with that nonlinear activation function, it can no longer be compressed.
Exactly. Because if we tried to do the same analysis here, when we substitute in, like in the second line, it's not just going to be weights which can be distributed. It's going to be some nonlinear function. Good question. Any other questions or confusions? Yes?
How do we know which function to choose?
Like which activation function?
Right.
That's a great question. The answer is it depends. Like different activation functions have kind of had their own like popular moment. Rectified linear unit is a pretty popular one. There are other variations on it that are pretty popular. But I would say like for a rectified linear unit, okay, so part of what it depends on is what's your goal, like what are you trying to do? If I'm trying to predict a continuous value, I'd probably want something like rectified linear unit because that y equals x is just a nice slope. But if I want to predict a probability, I might use something not necessarily like hyperbolic tangent, but something with similar shape which compresses values maybe to between 1 and 0, because that's going to give me a probability. But there are tons of different activation functions out there. So there's definitely a lot of customization. Good question. Yes?
So what exactly are activation functions?
Like, well, so we have an activation function. The reason it's called an activation function, where is it? The reason we call it an activation function is specifically because it comes at the end of a neuron, and it kind of comes back to, like, we're trying to, in some abstract way, kind of model this after a brain. So we're saying a neuron is activated if the activation function, produces some meaningful output. That's what the name comes from. So in this, we'll say like, okay, our node is activated if from the rectified linear unit there's some positive value, but if it's negative, then the output's just going to be 0. That's a non-active neuron. So you can think of the terminology in that sense. Any other questions? Okay. So the one last thing I did want to say was just that when we say deep learning, we're going to refer to neural networks that have one or more hidden layer, which I guess kind of goes without saying because our input layer, if we only had one layer, which was the input layer and the output layer, that would just kind of be linear regression with some activation function at the end. So when we say deep learning, we have multiple layers, often a lot with a lot of neurons. A lot of the recent advances have come from scaling up compute, like creating massive models. You'll hear like recent language models have been like, okay, hundreds of billions of parameters being like the number of trainable parameters like your weights or like your biases. So you can imagine like hundreds of billions of weights. So these get very large, hence deep learning. Okay, so what does it mean to actually learn, right? Because we said we are going to start with some arbitrary guess. Our original line was just, our weight 1 was equal to 1 and our bias was equal to 0. It gave us a garbage guess. So we initialize our weights as random numbers, and here in this example, from some input, let's say we have some image and we want it to, or we have some like previous stock prices and we want it to output the correct next stock price, we might have a random guess, which here is 11.2, but the real one that we want, the actual correct value is 17.2. So what do we want to do? We want to use the label to quantify how bad our guess was. And this is where I should mention, when we talk about deep learning, we're talking specifically about a branch of machine learning called supervised learning. What does that mean? Supervised learning means that when we're trying to train, we have some labels which tell us what the correct prediction or output is. So if we're trying to predict a class, we already know what the answer is. We're just trying to get the model to get to the right answer. So here, it's important that we have that label, 17.2, because with that, we can take whatever guess our neural network outputted, and we can say, okay, that was off by X amount. That was a really bad guess, or hey, that was actually a pretty good guess. And then once we have outputted our guess and we've quantified that, we then want to adjust our weights to somehow make a better guess, to decrease the difference between what we predicted and what the actual correct value was. That's going to be our general strategy. So how do we quantify what a guess is?